In this video here, we're going to take a look at trigonometric identities. Now we can use Moivre's theorem to derive trigonometric identities. And by applying the binomial expansion to cos theta plus I sin theta all to the power of n, we can express cos n theta in terms of powers of cos theta and sin n theta in terms of powers of sin theta. And we can also find trigonometric identities for sin theta to the power of n and cos theta to the power of n, where n is a positive integer. So let's just start then by deriving results for z plus 1 over z and z minus 1 over z. So let's just get started then with deriving results here for z plus 1 over z and z minus 1 over z. So to begin with here, if z is equal to cos theta plus I sin theta, then in that case 1 over z, which is just the same as z to the minus 1, is equal to cos theta plus I sin theta all to the power of minus 1. So by applying the Moivre's theorem here, we obtain that z to the minus 1 is equal to cos of minus theta plus I sin of minus theta, right? So this is just the Moivre's theorem here. And in that case then, once we simplify here, we obtain cos theta minus I sin theta. So therefore, we can see that z plus 1 over z is equal to cos theta plus I sin theta, so that's just z here, plus cos theta minus I sin theta, right? So that's z to the minus 1 there. And once we simplify here then, the I sin theta and the minus I sin theta, they just cancel. We just get left then with cos theta plus cos theta, giving us 2 cos theta. And similarly here then, z minus 1 over z is equal to cos theta plus I sin theta, so that's just z. We then subtract 1 over z, so 1 over z here is cos theta minus I sin theta. So in that case then, what happens here is the cos theta terms just cancel. So cos theta and minus cos theta, they just cancel. What we get left with then is I sin theta plus I sin theta, giving us 2i sin theta there. So that gives us the derivation then for z plus 1 over z and z minus 1 over z. So let's just have a go then at deriving the results here for z to the n plus 1 over z to the n and z to the n minus 1 over z to the n. So to get us started here then, if z to the n is equal to cos theta plus I sin theta all to the power of n, then this would just simply give us cos n theta plus I sin n theta. So in that case then, 1 over z to the n, which is just the same as z to the minus n, is just equal to cos theta plus I sin theta all to the power of minus n. And in that case then, if we apply Moivre's theorem here, we obtain the following. So z to the minus n is equal to cos of minus n theta plus I sin, again, of minus n theta, and that is equal to cos n theta minus I sin n theta, right? So therefore, we can see then that z to the n plus 1 over z to the n is just equal to the following here. So we have z to the n then, as we can see here, right, cos n theta plus I sin n theta. And we also have 1 over z to the n, so that's just this result here. So once we add those together, what's going to happen here is this I sin n theta will cancel with this minus I sin n theta here. And what that leaves us with then is cos n theta plus cos n theta. And once we simplify those, we obtain 2 cos n theta. And in a similar fashion here then, so for z to the n minus 1 over z to the n, well again we have z to the n here, which is just cos n theta plus I sin n theta. We then subtract this result here, so minus cos n theta plus I sin n theta. So what's going to happen here then is this cos n theta will cancel with this minus cos n theta here. And that leaves us with I sin n theta plus I sin n theta here. And again, once we simplify here, we obtain 2i sin n theta. So that gives us the derivation then of z to the n plus 1 over z to the n and also z to the n minus 1 over z to the n. So before we work through a couple of practice questions here then for trigonometric identities, let's just quickly summarize what we've found up to now. So to begin with here then, we have z plus 1 over z, which in this case just gives us 2 cos theta. And don't forget then, we have shown the derivation of this result here. And in a similar fashion here then, z minus 1 over z is just equal to 2i sin theta. So moving on now, we now have z to the n plus 1 over z to the n, which in this case gives us 2 cos n theta. And just notice here then, this result is very, very similar to what we obtained then for z plus 1 over z, which just gave us 2 cos theta. Okay. And then finally here, the very last result this is for z to the n minus 1 over z to the n, which in this case just gives us 2i sine n theta. And again, just notice that this result here is very, very similar to what we obtained then for z minus 1 over z, which just gave us 2i sine theta. Okay. Now, these results are not given in the formula book, so just make sure then that you do familiarize yourself with these results, or just familiarize yourself with how to derive these results. Okay. What I would recommend here is just remembering, for example, z plus 1 over z and z minus 1 over z. So, for example, 2 cos theta and 2i sine theta. And in that case, then, if you want z to the n plus 1 over z to the n, or for example, z to the n minus 1 over z to the n, in that case, all you need to do then is just add an n in front of your argument. Okay, so not particularly challenging to remember, right? But you aren't given them in the formula book. So it is something that you do have to memorize or be familiar with how to derive yourself. Okay, so there we have it. That gives us everything that we need here then for this introduction to trigonometric identities. Obviously, the basis of this video is just by using Moivre's theorem. Okay, so to finish with here then, let's just quickly work through a couple of practice questions here then for trigonometric identities. So let's just get started then with question 1 here. So for question 1, we want to use Moivre's theorem to prove this result here. So the first thing that I'm going to do here then is take cos theta. So we have cos theta plus I sine theta. And I'm going to raise this here then to the power of 4. Okay. And by Moivre's theorem here then, this will be equal to cos 4 theta. So cos 4 theta plus I sine, again, of 4 theta. Okay. Now this is useful because what we can do here then is apply the binomial expansion to the left-hand side here. And because we have cos 4 theta here on the right-hand side, well, what we can do then later on, once we've done the full binomial expansion here, is equate the real parts. Okay, and that would give us an expression here then for cos 4 theta, and hopefully we'll obtain this result here. So to get started then, as we've already mentioned, right, let's just now use the binomial expansion. So let's just make a note here. So now use the binomial expansion. So we're going to use the binomial expansion here, and I'm hoping the binomial expansion by this point is pretty straightforward. So what I'm going to get here then is cos theta. We get cos theta raised to the power of 4. We then get 4 choose 1. So 4 choose 1. We then times this by cos cube theta. So cos cube theta. And then we times this here by I sine theta. Let's keep going here. So now we get 4 choose 2. So 4 choose 2. We now times this by cos squared theta. So as you can see then, the powers of cos theta will reduce by 1 as we go along. And the powers here for sine theta will increase by 1 as we go along. Okay, or I should say I sine theta here really. So cos squared theta, as we've already mentioned, like so. And we now times this here. So make sure you do the full result here, or the full expression I should say. So I sine theta all squared. Okay, let's keep going. We now get 4 choose 3. So 4 choose 3. We now times this by cos theta. So cos theta. And we times it by, it's I sine theta to the power of 3. And then finally here, we get 4 choose 4, which is just 1, but we'll write it down anyway. So 4 choose 4. And we now times this by I sine theta to the power of 4. Okay, so let's just simplify here then. Well, we can't do anything with the cos theta raised to the power of 4. So that's just cos theta to the power of 4. 4 choose 1 is 4. So we get plus 4. I've also got cos cube theta, and then we times this by I sine theta. So altogether then, what I've got here is 4i. So we'll put the imaginary unit with the 4 here. So we get 4i cos cube theta sine theta. Let's keep going here. So now 4 choose 2 is 6. We then got cos squared theta, so I've got 6 cos squared theta. And then we times this by I squared sine squared theta. Now, I squared, you should be aware then, I squared is -1. So in that case, then what I've got here is 6i squared cos squared theta sine squared theta. But given that I squared is equal to -1, what I've got here then is -6. So I've got -6 cos squared theta sine squared theta. Hopefully nice and straightforward up to now. So like I said, right, we're just simplifying as we go here. So let's keep going then. So we now have 4 choose 3. We times that by cos theta, and then we times it by I sine theta, all to the 3 here. Now 4 choose 3 gives us 4. We then times 4 by I cubed here. So I cubed then, this is equal to -1 times by I, so we get minus I there. So once we simplify this multiplication here, then what we get is -4i. So -4i, we times that by cos theta. We times that by cos theta, and then we times that by sine cubed theta here. Okay. Like so. And then finally here for the very last term, nice and straightforward. 4 choose 4 is 1. We then times this here by I sine theta, all to the 4. So what I've got here then is I to the 4. So I to the 4 is just the same as I squared times by itself again. So -1 times by -1 here just gives us 1. So in that case then, the final term here just simplifies to give us sine theta all to the 4. So sine theta to the 4 there. Okay. And we're nearly done at this point now. All we need to do here then is equate the real parts. So we just make a note here then. We're now going to equate the real parts. So now equate the real parts here. And we do also need to use a trigonometric identity as well here. So we're also going to use them. So, and use the fact that sine squared theta, so sine squared theta is equal to 1 minus cos squared theta. Okay. Now, when we say that we're equating the real parts here then, what that means is we get cos 4 theta. So cos 4 theta is identical to, so basically, from this binomial expansion here, we want anything that doesn't include the imaginary unit. So we're going to exclude this term here. We're also going to exclude this term here, but include everything else, right? So we get cos theta to the 4. So cos theta to the 4. We exclude this one here, right, as we already mentioned. We then get -6 cos squared theta times by sine squared theta. So -6 cos squared theta times by sine squared theta. We exclude this term here, and then finally we get sine theta to the 4. So plus sine theta to the 4. Okay. And now all we need to do to finish with here then is just use this trigonometric identity, right? We're going to use this trig identity here. So wherever you see a sine squared theta, just replace that with 1 minus cos squared theta. So cos 4 theta here is identical to, so we can't do anything with the cos theta to the 4 here. So cos theta to the 4. We now have -6 cos squared theta times by sine squared theta. So just replace sine squared theta here with 1 minus cos squared theta. So -6 cos squared theta. Then we times this by 1 minus cos squared theta. Like so. And now for the sine theta to the 4 here, so just be careful with this. So sine theta to the 4 is just the same then as sine squared theta. So sine squared theta all squared. Okay. So in that case then, what we get here is 1 minus cos squared theta all squared. Okay. So let's just expand here and simplify them. So cos 4 theta is identical to, we can't do anything with this at this point. So cos theta to the 4. I've then got -6 cos squared theta times 1. So we get -6 cos squared theta. I've then got minus 6 cos squared theta times minus cos squared theta. So just be careful of your signs here, right? So we get plus 6 cos theta to the 4, like so. We've then got 1 minus cos squared theta all squared. So this is just expanding double brackets here. So if you expand these double brackets here, then what you should get is 1. We get plus 1 minus 2 cos squared theta. So minus 2 cos squared theta. And then finally, plus cos theta to the 4. Like so. And then finally here, one final simplification here then. So cos 4 theta is identical to, so we've got cos theta to the 4, 6 cos theta to the 4, and then finally cos theta to the 4. So once we simplify those, we get 8 cos theta to the 4. So 8 cos theta to the 4, like so. What else do we have here then? So I've got minus 6 cos squared theta. We've also got minus 2 cos squared theta here. So that would give us minus 8 cos squared theta. So minus 8 cos squared theta. And then finally, we also have this plus 1 here. So plus 1. And just notice then, this gives us the exact result that we wanted here, right? So as required then, and question complete. So as required there. And there we have it. So that gives us the solution there to question 1. So let's just move on to the very last question here then. So we have question 2. And again, for question 2, all we want to do is use the Moivre's theorem to prove this result here. Now, given that we're looking at powers of sine theta and cos theta, in this case sine theta, what we need to do then is use the results for z plus or minus 1 over z. And in this case here then, given that we're looking at powers of sine theta here, we're going to use, let's just make a note here then. So we're going to use z minus 1 over z is equal to 2i sine theta. So 2i sine theta there. Okay. So to begin with then, given that we have sine theta to the 4 here, we take z minus 1 over z and raise that to the power of 4. We've got z minus 1 over z all to the 4. So in this case here then, raise the right-hand side also to the power of 4. We've got 2i sine theta to the 4, which once we evaluate this here then, we get 16i to the 4. So 16i to the 4 sine theta raised to the 4. Like so. Well, you should be aware then, and we demonstrated this in the previous question, right? I to the 4. So I to the 4 is just 1. So what I get here then is 16 sine theta to the 4. Okay. So what we're going to do now is use the binomial expansion here then on the left-hand side. Okay, so let's just make a note here. So use the binomial expansion. Use the binomial expansion here then. So if we use the binomial expansion here then, what do we get? So to start with, we get z to the 4. We get z to the 4. We then get 4 choose 1. So 4 choose 1. We then times that by z cubed. So z cubed. And we times it by minus 1 over z. So minus 1 over z, like so. Let's just keep going here. So we now have 4 choose 2. So 4 choose 2. We times that by z squared. And then we times this by minus 1 over z all squared. So minus 1 over z squared, like so. Let's just keep going. So we now have 4 choose 3. So 4 choose 3. We times that by z. And we times it by minus 1 over z all cubed. Like so. And then finally here we have 4 choose 4, which is just 1, but I will write it down anyway. So 4 choose 4. And then we times this here by minus 1 over z all to the power of 4. Like so there. Okay. Let's just simplify this here then. So obviously we can't do anything with this z to the 4 here. We've got z to the 4. 4 choose 1 is 4. So I've got 4 z cubed. So plus 4z cubed And then we times this by minus 1 over z. Okay, so you could just simplify this all as one line. I'm going to do it as 2 here just so you can see my full working. Let's just keep going here. So 4 choose 2 is 6. I get 6z squared. So 6z squared. And that times this here by minus 1 over z squared. So that just simplifies to give us 1 over z squared here. So 1 over z squared. 4 choose 3 is 4 again. I get 4z. Then we times this here by minus 1 over z all cubed. So that gives us minus 1 over z cubed there. Okay. I'm nearly done here then. So 4 choose 4 is 1. Then we times this by minus 1 over z to the 4 here. Okay, which if we just simplify here, just gives us 1 over z to the 4. Okay. So if we just simplify this line here then, and as I said, right, you could have just done this all in one line, but just so you can see the full working here, I get z to the 4 again. 4z cubed times minus 1 over z, so that gives me minus 4z squared. I've then got 6z squared times 1 over z squared, so the z squared just cancel, right? I just get plus 6 there. So plus 6. 4z times minus 1 over z cubed, so I get minus 4z to the minus 2 there. So minus 4z to the minus 2. And then finally here we have plus z to the minus 4 there. Okay. What we want to do now is group the relevant parts together. So what I mean by that then is we can group z to the 4 and z to the minus 4 here. So I've got z to the 4 plus z to the minus 4, like so. I've then got minus 4 lots, so minus 4 lots here of z squared plus z to the minus 2. So z squared plus z to the minus 2, like so. And then finally, we just got this plus 6 here, right? We can't group that with anything, so it's just on its own at the very end. Okay, so hopefully that makes sense what I've done here, right? Just grouping z to the 4 and z to the minus 4, grouping the minus 4z squared and the minus 4z to the minus 2 together. Okay, so at this point here now, what we can do is use this result here. So we can use then z to the n plus 1 over z to the n. And as you can see then, this is why we've grouped these relevant terms together here, because we're now going to use this result. And you should be aware then that z to the n plus 1 over z to the n is equal to 2 cos, so 2 cos n theta. Okay. So what I've got here then is z to the 4 plus z to the minus 4. So using this result here then, what we get is 2 cos 4 theta. I do this underneath then. We get 2 cos 4 theta. Obviously my power here is 4, right? So we get 2 cos 4 theta. I've then got minus 4. So minus 4 bracket. So z to the 2 plus z to the minus 2. So that's just going to be 2 cos 2 theta. So 2 cos 2 theta. And then finally here, plus 6. Okay. So plus 6 there. So if we just simplify this here, then what do we have? So 2 cos 4 theta, can't do anything with that. So 2 cos 4 theta. Then we get minus 8 cos 2 theta. So minus 8 cos 2 theta. And of course, don't forget your plus 6 here. So plus 6 there. And we just go to the top here again. What do we have now? Well, what I've got here then is 16 sine theta to the 4. So 16 sine theta to the 4. And this here then is just equal to this, right? So in that case then, 16 sine theta to the 4 is equal to 2 cos 4 theta. So 2 cos 4 theta minus 8 cos 2 theta minus 8 cos 2 theta plus 6. Okay. So given that they've got sine theta to the 4 here, there's no coefficient. Well, there is a coefficient, but it's 1, right? So clearly what we need to do here then is divide through by 16. So in that case, then we get sine theta to the 4. So in that case, then I get 2 over 16, which is 1 over 8. So I get cos 4 theta over 8, or 1 over 8 cos 4 theta, whichever you prefer. Obviously, they're just equivalent. So 1 over 8 cos 4 theta. So I've then got minus 8 divided by 16. So that's minus 1 over 2. So minus cos 2 theta over 2, or minus 1 over 2, whichever you prefer again. Like so. And then finally 6 over 16. So we can write that as 3 over 8 there. So plus 3 over 8. Okay. And just notice then for the very last solution here, or the desired result here, they factor out 1 over 8. So if we just do that as well, what we get here then is sine theta all to the 4 is equal to, so factoring out the 1 over 8 here, we get 1 over 8 bracket. So I get cos 4 theta. That's absolutely fine. That's what we want. So cos 4 theta. I've got minus 1 over 2 cos 2 theta. So once we factor out the 1 over 8, I then need minus 4 lots of that. So minus 4 cos 2 theta. And again, that's perfect. That's what we want here. So good stuff. And then again, once we factor out a 1 over 8 here, we just get plus 3. We get plus 3 there. So just notice then, once we factor out the 1 over 8, we get the exact result that we wanted here, right? So as required then, and question complete. So as required there, perfect. And there we have it. So that gives us the solution then to the very last question here, question 2. And that actually brings the end of this video here on trigonometric identities.